So we know this artificial neural networks, they are used in various fields from image recognition to speech recognition and natural language processing. And they are inspired by the structure and function of human brain, and their ability to learn and make decisions is thanks to the intricate connections between the neurons. But for a neuron to fire and send information to another neuron, it needs a mathematical formula to determine when to activate. And there is when the activation function comes into play. So today we'll explore the importance of this activation function. What are the different types of activation functions which are used to make this neuron pulse or fire? So let's understand what is activation function. So this activation function, it's a mathematical formula that determines whether a neuron in an artificial neural network should fire and send information to another neurons based on the inputs it receives. So this activation function will take the weighted sum of the inputs and a bias term as input and outputs a value that will determine whether or not a neuron should be activated. So this output value can be real number or a probability depending on the type of activation function used. So in simple terms, this activation function, it's like a gate that either opens or closes based on certain conditions. So here this input data will go into this gate, and the activation function will decide whether the gate opens or closes, allowing the output to pass through or not. So now the next question would be why we need this activation function. So these activation functions are used in artificial neural network to introduce non-linearity and decision making capabilities. So think of them like giving a neural network a set of tools that allow it to think and decide in a complex manner. So without activation functions, neural networks would only be able to make linear decisions, which would severely limit their ability to solve real world problems. So let us understand this by an example. Imagine you want to build a neural network to predict the price of a house based on its square footage. So without an activation function, the network would be able to make a linear prediction, such as the price of a house is directly proportional to its square footage, right? This might be a starting point, but it would not be able to account for other factors that influence the price of house, such as its location, its age, condition, so on. So by introducing an activation function, you enable your neural network to make non-linear predictions. So for example, the network might learn that house with a large footage in a high demand location would be worth significantly more than a house with the same square footage in less desirable area. So here this activation function will act like a filter that decide how much influence each factor such as square footage or location should have on the final prediction, which allows the network to learn complex relations between this input and output and make it more powerful and versatile. So in short, these activation functions are used in artificial neural networks to introduce non-linearity and decision-making capabilities, so which enable them to make more accurate predictions and learn from complex data. So let's understand the types of activation function. So each activation function would serve a specific purpose. So let's start with the sigmoid activation function. So this sigmoid activation function, it squashes an input value between 0 and 1, and it's basically used in binary classification problems as the output can be interpreted as a probability. And its formula is like this. So for example, suppose you are training a neural network to recognize whether an image contains a cat or not. So here the sigmoid function can be used in the output layer to output a probability between 0 and 1, indicating the confidence that the image contains a cat. But this sigmoid activation function has a disadvantage, for it tends to produce vanishing gradient during backpropagation in deep neural networks. Why it happens? Because the gradients get exponentially smaller as they propagate backward through layers with sigmoid activation function, which makes them difficult for the network to learn effectively during training. So as a result, these deep neural networks with sigmoid activation functions, they require more training epochs and not converge as quickly as networks using other activation functions. Then comes this hyperbolic tangent. It's somewhat similar to sigmoid, but here the value will lie between the -1 to +1. So it's less prone to vanishing gradient problem, and it is used in hidden layers. So here, for example, in a neural network for natural language processing, so this hyperbolic tangent function can be used in hidden layer to learn complex relations between the words, phrases and sentences. So this hyperbolic tangent activation function somewhat similar to sigmoid, but it has few other advantages. For example, here this range lies between -1 to +1. And the key difference is that the gradients in back propagation are not vanishing as quickly with this 10H, which makes it more effective for training deep neural networks. Why so? Because the slope of 10H is relatively high around the origin. So while the sigmoid function has relatively low slope. So as a result, this 10H is often preferred for hidden layers as it helps maintain the gradients and speed up the training process. Now next comes the rectified linear unit activation function. It's simple and computationally efficient and helps to alleviate the problem of vanishing gradient. It sets all the negative values to 0 while positive values remain unchanged. For example, imagine you are training a neural network to classify handwritten digits. So there the ReLU function can be used in hidden layers to learn relevant features from the input images such as edges, corners and curves. So compared to the sigmoid and 10H, this rectified linear unit has some advantages. For example, first it is computationally efficient because it simply outputs the input if it is positive, otherwise it says 0. And this simplicity results in faster computations and less memory usage. Secondly, it helps to elevate the vanishing gradient problem that sigmoid and 10H suffers from. So when the gradients flow backward through a network with ReLU units, they do not become exponentially smaller as they do with the sigmoid and 10H functions, which allows for the faster and more stable training, especially in deep neural networks. And lastly, these ReLU units are more biologically plausible as they mimic the firing behavior of neurons in the brain, which either fire or remain inactive. And this simplicity has contributed to the widespread adoption of this ReLU in modern deep learning architectures. Now next comes this Leaky ReLU. Now it's also a variation of this ReLU, but it allows small negative gradients to flow through the network, which might help it in mitigating the dying ReLU problem. For example, in a neural network for image classification, the Leaky ReLU function can be used to learn complex features from the input images such as the shapes and texture of objects. So in the ReLU, neurons with negative inputs are dead, means they will no longer contribute to the output since their output is 0. But then in this Leaky ReLU introduce a small positive slope for negative inputs as well, like here. So there is some slope here, right? So in contrast, this Leaky ReLU has introduced a small positive slope for negative inputs, which allows them to contribute to the output and prevent the neurons from dying. So which makes this Leaky ReLU more robust, especially in the early stages of training when the gradients are not yet well established and the risk of dead neurons is higher. Now next comes the exponential linear unit or the ELU. Now this ELU, it's similar to the ReLU but for negative inputs. It has negative slope that helps elevate the dying ReLU problem. So here, for example, in a ReLU neural network for speech recognition, it can be used in hidden layers to learn patterns in audio signals and extract the relevant features. Now, how it is better than other activation functions? So first, it addresses the issue of dying neuron, similar to the Leaky ReLU. Along with this, it has faster mean output growth for negative inputs, which helps maintain the gradients during back propagation and improves training stability, especially in deep neural networks. And secondly, this ELU has a lower mean output than ReLU and its variants, which can be beneficial when dealing with vanishing gradient. So these negative outputs are scaled by a factor that is less than 1, which allows the gradients to flow efficiently through the network. Then comes the softmax activation function. So this softmax activation function is mainly used in multi-class classifications. So here it takes the vector of real numbers and outputs a vector of probabilities that sums up to 1. So its formula is like this. So for example, in a neural network for image classification with multiple classes, the softmax can be used in the output layer to output a probability distribution of other classes, indicating the confidence of the network for each class. So this softmax activation function is commonly used in the output layer of multi-class classification problems. So where it transforms the output of previous layer into a probability distribution and the sum of all the outputs is 1, which makes the output comparable and interpretable. Also, it allows the network to be trained using a cross entropy loss function, which makes it suitable for multi-class classification. But apart from this advantages, it has the disadvantage, for it can be computationally expensive, especially for the large scale problem with many classes. Why happens this? Because it computes the exponential of each element in the input factor before normalizing them. So in addition, when dealing with the numerical underflow issues, the softmax may not be suitable for input vectors with vastly different magnitudes. So next comes the softplus function. So this softplus function is differentiable approximation of ReLU, and it's less prone to dying ReLU, and it's used in some deep learning algorithms. So where its formula is like this. So for example, in a neural network for facial recognition, the softplus function can be used in hidden layers to learn relevant features from the input images such as position, shape, and size of facial features. Then comes parametric rectified linear unit, or PReLU. So it's a drop-in replacement for ReLU where a learned parameter is added to the input before applying the ReLU function. So this parameter will adjust the slope of the linear part, which allows the network to learn the optimal slope. So this PReLU is basically an improved version of ReLU. So when we look at its formula, here this alpha or the A parameter, it's generally a number between the 0 and 1. So, and it is generally relatively small, such as few zeros. So if this AI is 0, it becomes ReLU, right? If this AI is greater than 0, it becomes leaky ReLU. And if it is a learnable parameter, it becomes parameterized ReLU. For example, consider a neural network for image classification. So here this PReLU function can be used in the hidden layers to learn the features from the input images, and the learned parameters can adapt to each neuron's needs, enable the network to learn more complex features compared to a fixed ReLU function. So basically this PReLU offers a good balance between the computational efficiency, robustness against dead neurons, and improve the training stability, which makes them possible or the popular choice for deep learning applications. And then comes the swish or the self-gated function. So this swish is a smooth and monotonic activation function which interpolates between the linear function x and the sigmoid function. And the function aims to address the vanishing gradient problem and provides a smoother derivative than ReLU. For example, imagine a neural network for speech recognition. So here the swish function will be used in hidden layers to learn patterns in the audio signals, extract the relevant features. And the smooth derivative of this swish function will help elevate the vanishing gradient also. So this major advantage of swish activation function is its unbounded nature, and its derivative always greater than 0. Also, it has smoothness. So this swish prevents a vanishing gradient problem by avoiding saturation, while its smooth nature helps in optimization and generalization. So additionally, its learnable gating parameters offers flexibility, which makes it a powerful alternative to traditional activation functions. So to summarize this, we can say that these activation functions are tailored to address different challenges in ANN. So by selecting the appropriate activation function, you can optimize the performance of your network. Thank you.